Let's get going again. We forgot to do something fun during break, other than have a break. So that's just one less time of doing something fun. Sorry. Maybe we'll do something fun at the next break.
What's our prediction?
What's that?
What's our prediction?
The prediction is that we might have fun in the future at a break, but we probably won't. So I was thinking of making it also a little more technical, which sounds like such a teacher thing to say, as opposed to what's your favorite like sub shop, which we have asked before in class. But we'll find out at the next break. Until then, the mystery continues. So let's go at this. We have to get back to this translation process. We actually haven't even talked about all the stuff that has to happen during a translation. I will also, by the way, talk about some administrative stuff at the next break, but let's just get back into work right now while we're still able to. So any questions about this? Does it make sense what's happening? We have a virtual address. We take a piece of the virtual address, which is the VPN part. And as we saw, I think it made sense when we saw it. We saw that, the virtual page number is just some bits that don't change on the given page, right? That when bits of the address on that page that don't change. That's how we know it's virtual page 0, for example. And what we're doing is we're just changing those bits so as to get a physical address where the data actually resides. Pretty simple process, hopefully. Now, somebody pointed out during break, good question, which is, hey, it looks like in this address space that I can do a null pointer dereference. Is that true? The answer is yes, you can, because we've defined here address 0 is part of our address space, and what is a null pointer but the 0 pointer? So in this simplistic system that we're looking at, the null pointer is just probably some code sitting there. So if you dereference a null pointer and there's some code there, what will happen is you will get the bits that represent the code. In a short order, we will do a more sophisticated address space where we explicitly don't map the 0 page so as to generate a fault when we happen to access a null pointer dereference. That's just for kind of debugging utility, because a lot of times we forget to initialize pointers, and when we do that, they're often 0, not always. And when they're 0, then they will cause some kind of bad stuff to happen, and we'll notice. It'll help us. But here, we're out of luck. Does that make sense? It's a good kind of interview question, like why does a null pointer why does that cause a fault to occur? And it has completely to do with how our virtual memory system is set up and which pages we allow access to and which pages we don't. So speaking of which, let's make sure we understand another part of our example. We have this page here that's not in use. And what that means is addresses, we know that 0 through 7, 8 through 15 are all valid, but 16 through 23 in this address space, this tiny address space of ours, are not valid. So it means when we generate a reference to 16 or 17 or 18, 19, 20, 21, 22, 23, what we should have is something, we shouldn't be able to get some data there. Something bad should happen. We should get some notice. And what we'd like to have happen, of course, is some kind of exception, or you might think of it as a fault, where the address causes something bad to happen. And for us to know that, we have to have some information in the page table itself. And so here was our page table, this big thing here, which just has 4 entries. We know that part of it is a page frame number, but what we're also going to do is we're going to have some other bits in there that are going to help us out. And a pretty natural bit to have is something kind of like a valid bit, which tells us whether or not that part of the address space is okay for us to access. So here, we're going to make it 1, 1, 0, and then 1, indicating that pages 0, 1, and 3 are all accessible and valid, and that page 2 here is not, and their valid bit is 0. So that means whenever we somehow go to access that page and go to do a translation, if you generate an address like that, we want the hardware to notice that, generate an exception, and then jump to the OS and likely say kill the process or something like that. So we'll talk about that machinery in more detail shortly. Any questions about that? Does that kind of make sense? So let's start talking about a couple different things. We have to figure out, I mean, we talked about translation kind of theoretically or conceptually is the right way to say that. We've talked about conceptually what's happening. You have a page table for a given process. If you switch to different processes, you're going to have to a different process that's running, you will be switching to using a different page table. But we want this to be an efficient interaction. In fact, we don't generally want the OS to be involved with translation. What would happen if you have to talk to the OS every time you did a translation? It would be wildly slow. It means your computer program would run hundreds or thousands or millions of times slower. So we have to understand how translation occurs. And because remember we're building this limited direct execution model where we basically want to allow the hardware to run and do most of the stuff, hardware for efficiency, and we want to limit it so that you can't just do anything. So that's our same model that we have in place. And with a page table, what that means is that the hardware does most of the work. So how does it do that? Well, we have our physical memory. And we have some pages in use there. I guess I was supposed to do at least 8 pages or something. 0, 1, 2, 3, 4, 5, 6, and 7. And we already said a few of those physical pages were in use, so let's be consistent. Pages 1, 5, and 4. So these are in use. But the OS is going to use some of the memory too, and it's going to use, let's say it uses some part of this memory for this page table of our one process. Let's call it process 0. When process 0 is running, the hardware is going to want to know a couple things in order to be able to do the translations for us and not have the OS involved at all. So the question is, what does the hardware need to know? Well, we know that the page table is here. We know that our pages are here, here, and here. At 1, 4, and 5, and it's somewhere in page 0. Let's say it's at address, 0, 1, 2, I don't know, address 3 or something like that. So what does the hardware need to know in order to do a translation for us? What are all the things the hardware needs to know to do translations? So we're running this process. We do an instruction fetch. Immediately, this is going to become a problem. Instruction fetch, first thing we do, it's a memory reference. So what are we going to do? What do we need to know? Yeah. Yeah, you need to know the location of the page table, right? The hardware needs to know where it is. In this case, it's right here. What else does it need to know? That's it. If you just somebody, let's say you're the CPU. Pretend you're a CPU. This is something I'm sure you do from time to time because you're into computers. You're like, what would it be like to be a CPU? So many ALUs and parallelism. No, you probably don't think like that. But if you did, in this case, you would be thinking, what do I need to know to do a translation? Someone gives me a virtual address. What do I need to know? I need to know where the page table is. Good. What else do I need to know? Yeah. Yeah, you need to know a bunch of details of the system, like, for example, the page size. You need to know, well, certainly the address size, things like that. In general, in fact, you need to know, so page size is a good example. What about when we're looking here? We looked at our page table over here. What do we know? What do we need to know about that in order to do a translation? Yeah. Well, yeah, if it's valid, in other words, we need to know the structure of the page table, right? One of those things is it which bit tells us what's valid, which bits tell us, oh, these are the page frame number bits. We need to know the structure of that page table. So page size and structure of the page table itself, or structure of a page table entry. We have to know all that stuff. And on many modern systems, like x86, for example, those structures, everything that we talk about here is defined by the architecture. The hardware says a page table should look like this, and we should have some method for locating it, and these are the exact details of page size and everything like that. So there's no great freedom for the OS designer who has great ideas about how to build a data structure. Rather, it's defined by the hardware. It's because the hardware needs to know this information in order to do this translation. So let's talk about the location. The location piece implies something, which means that there's a per CPU register that is going to, at any moment in time, hold the address of the page table of the currently running process. Okay, and what type of address is that? It's a physical address. In our imagination so far, we haven't yet added a virtual address space for the OS itself. We will actually do that, but for now we just assume it's a physical address, and that's fine. So it holds a physical address of a page table of the currently running process. And if this per CPU register is really appropriately named, it's called the page table base register. And we will call this, because we abbreviate everything for confusion's sake, the PTBR. So the PTBR holds the base of the PT, which has a bunch of PTEs in it, which allows us to translate VPNs into PFNs, which in the end allow us to translate VAs into PAs. Okay, who can repeat that? Anybody? No? Okay. Maybe actually all of you. You probably could. But in any case, the point is we have to kind of get a little bit of these terminology into our heads. So in a system with multiple CPUs, which we don't talk about a lot, but maybe we'll talk about at the end of class if we have time, we would have on each CPU core, we'd have a PTBR, and it's going to help us with the translation. Okay? So the PTBR plus just the static knowledge of page size and the contents of page table give the hardware enough information to do a full translation. So let's go back to our example here. We had our table here, which had these contents in it. Let's just replicate that down here. So here's our page table. Had valid, valid, not valid, valid. Had 1, 5, and 4. It doesn't matter what these bits are because the page is not valid. And this is in memory somewhere. Let's say it's at address, I don't know, like 4 or something like that in physical memory. That's a physical address. So that means when we start running this process, what we do is we set PTBR to 4. And at that point, we can run this process. So you can imagine this PTBR is getting changed somewhat frequently when the system's running, because as we switch from one process to the next, we need to switch from one page table to the next. So this is a value that changes upon, say, context switching. Okay, but for a given running process, it's going to remain constant. And now what that allows us to do is when we're given a virtual address, which we need to translate, and for simplicity, let's say we know the size of a page table entry. Let's just say it's 1 byte. So the size of our whole page table for this process in this toy example is 4 bytes, right? This is 4 bytes total. And when we need to do a translation, what we now need to do is we need to figure out the physical address of the desired page table entry. So if we picked an address, let's say pick a different address. Let's say we have address 20010, something like that. This is our system with 8-byte pages and 4 of those for a 32-byte address space. This is our entire virtual address that gets presented to the system. What we then do, well, this is one of those cases where it's it's a bad example. So I'm going to change it on the fly. Let's change it to back to something more like what we had before. Or let's just do all the way at the end. So if we pick an address like this, we know that this part of the virtual address is the virtual page number, which is page number 3, right? This is 0, 1, 2, and 3. Virtual page 3 is indeed valid. But let's say we want to figure out the physical address. This is what the hardware is doing, the physical address of the desired page table entry. What is that? It's the PTBR plus what? So remember, we want just the address of this page table entry right here. So if we think about the physical memory, oh, sorry, I said it was at 3 before, and then I changed it to 4. So let's go ahead and draw that in here a little bit carefully. So in physical memory, we have 4 bytes that are dedicated to our page table, bytes 4, 5, 6, and 7. So this is the first 0th entry here, this is the first entry, this is the second entry, and this is the third entry. The PTBR for this example is 4, which is it's called the base register because it's the beginning of the page table. I did promise that it only gets worse. This is the easy part of this discussion. It gets much more detailed and much worse. We're trying to reference the third entry. What address is the third entry? What physical address is that? 7. How do we get that? We get that by taking the page table base register plus, yes, plus the VPN, and there's a hidden part of that because I made it easier here, plus the size times the size of the page table entry. The page table entries here are just 1 byte, so it's an easy thing where we just add the VPN. This is what the hardware is doing. Every time you give it an instruction, it's going to take the page table base register, it's going to add the VPN times the size of the page table entry, and now it knows what address in order to get the page table entry, the PTE, that it's interested in. Pretty exciting. It gets even more exciting momentarily. It's just like it will blow your mind. This is not true at all. It's going to be very similar to what I'm talking about right now. But the point is, here you have an address. Now what do you have to do? You have to go load the page table entry. Then, so that's step 1, calculate the address. So that's what we did here, of the page table entry. Then load the page table entry. That goes to memory. It's slow. Then actually do the translation. In this case, that means take this address, the VPN, and replace it with the corresponding PFN, which is in this case 4. So we go here and we take 11010 and we turn the 3 into a 4 because that's what the page table tells us to do. That's what's in here. These bits we just take directly and we end up with our physical address. And remember, all we were trying to do is load a byte of information. Then we go ahead and do the load of the data itself. So that is this painful process of, we've added a page table, which is translation information for every page of our address space, which is potentially very large. Here it's small, it's just 4 pages. And what we do each time that we refer to memory, instruction fetch, or explicit load, or explicit store, or more complex instructions that do all sorts of crazy things, we have to use, the hardware is going to use the page table base register to calculate the address of the page table entry, then go ahead and load that page table entry, do the translation, which is fast, right? It's just moving some bits around, and then do the load of the data. The questions about that? It's really important to understand that, yeah.
Can you explain again how it goes
Yeah, of course. So how it goes from 3 to 4 is we know that we're on virtual page 3. So what we need to do is consult our page table. Our page table is, it's like a data structure where you give it a virtual page number and it's supposed to spit out a physical frame number. So the way we do that is we say, oh, 3, what we'd like to get is the third entry of this array. And so the way we get the third entry, this is just array index address calculation. You take the page table base register plus the VPN times the size of the page table entry. That is going to give us this entry. We get that entry out. Then we simply directly take those bits, 4 or 100. That's our physical frame number, which then we just directly put into the physical address. So this is the physical frame number, which came from the page table entry, PTE. Ugh, so much detail. Does it get better ever? No. It gets much, much worse. There's so much more that's going to happen in this process before we get through an actual translation. Yeah. Great. So what's going on with the PTBR? Like I said, just by name, it's the page table base register. It's just telling the hardware for this process, this is where the page table is. When we switch to a different process, we're going to use a different page table. And so that page table is an array in memory, all contiguous, and it says this is the beginning of it. So then the hardware knows when it gets an address to translate, it knows how to take that VPN from that address and use the base register to combine and say, oh, I need this entry. This is the page table entry that I need to tell me the translation information. Yeah. This picture, oh, sorry. Here? Below or above? Above. Yeah, so the PTBR here is an address which just tells us, oh, this is the page table right here. This is the page table with entries 0, 1, 2, and 3. It's just a 4-byte page table because it just has 4 entries. If we had multiple page tables, they would be at other locations, like here perhaps. Here could be another page table. It's just telling us where the page table begins in physical memory. Does that make sense? Yeah. Yes, great point. So if we have 100 processes, somewhere in this memory we'd have to store, we don't have enough room, but if we have 5 processes, yes, here's another page table, here's another page table, here's another page table, and here's another page table. And that's our simple model at the beginning. We have 1 page table per process. It's a completely realistic model. Like I said, x86 has that exact model, 1 page table per process. Is that the only way to do it? No. We'll talk about other ways to do it too. Does that answer your question? Yeah.
Is the size of the page table entry stored in a register somewhere?
Okay. The size of the page table entry in this thing that we looked at so far is just known. It's just defined by the hardware. The hardware says a page table entry looks like this. These bits are page frame, physical frame number. This bit is the valid bit. There's some other bits in there. Can you guess what other kinds of bits would be in there? What else would be in some sort of, like when I'm accessing memory, what might I want to know or have in a page table to maybe limit access? Yeah. Yeah, some sort of protection or permission bits. So you might have read, write, execute permissions. We haven't talked about that. Maybe we'll get to that a little bit later. Good questions. Other questions? Yeah. Can you ask what? Can you ask 3 questions? I don't know. It depends on the quality of the questions. I mean, it's a lot to ask, right? Now it's 4 questions. Yeah, so right now what we're doing is we're assuming the OS just resides in physical memory magically. Eventually we'll see the OS actually wants to live in a virtual space too, and how it's going to have addresses translated, and that's just part of our theme of making things worse and more complicated. That also, it turns out to be the way that for years that, what am I going to say? No, I'm going to say, eventually I'm going to lead to, this relates to meltdown. The way that virtual address spaces are constructed is actually the kernel lives in like a part of every process's address space in a kind of a protected way. But it turns out that wasn't as protected as we thought it was, and that's what led to the meltdown problem. So we're almost getting to the point where we can understand that problem. So question 1, for now, no. Eventually, yes.
How does, when you switch contexts,
Yeah.
how does the processor get where this process is PTBR?
Oh, great question. Let's see if someone else can answer it. So the question is, the PTBR clearly must be switched when we've been running process 1 and we're using the page table of process 1. Then we want to switch to process 2 and use the page table of process 2. Clearly, two questions actually relate to that since we're the question multiplier over here. One question is, we have to change the PTBR. Well, how do we do that? Well, we have to use some kind of instruction. What do we know about that instruction? Privilege. It has to be a privilege instruction, right? You can't just allow anybody to change the page table base register. Otherwise, what they could do is set up a page table where they can access all of memory and then just point the processor to it and then access all of memory. So we need a privilege instruction to change PTBR. Let's just write that down. So some PTBR details. Privileged to update. Privileged. Oh, Christ. How about this? Restricted access. Restricted. Not all can update. So then your question is, how do we know what PTBR to set to when we're switching from one process to the other? Well, the other detail is, of course, we still have some sort of, process table, some sort of thing we're tracking it where we have per process information that we're tracking. Like we're tracking things like, are you running or are you ready to run or are you blocked on I/O? And we might be, when you're switching between processes, you might save and restore some registers in this per process context information. And what we also do in there is we will save the PTBR into here when you're not running. So save and restore PTBR is something that the OS must do. So the OS has a data structure per process, and for every process we're going to certainly save the PTBR when we switch away from that process and then restore it onto the CPU of the running process. Does that make sense? Did you have a third question, or was that it?
Oh, I was so like for every instruction that we want to run,
Yeah.
the processor is forced to run at least every one.
Yeah, you're pointing out here there's a lot of work going on. I wouldn't use the term instruction, but logically what you're saying is kind of correct, which is, yes, I'm doing a instruction fetch, and that means I thought that was doing, from my understanding of the von Neumann memory model, every instruction I have to fetch from memory, I thought that was doing one memory access. But now, because of this abstraction, we're doing two memory references and some other work, to try to twiddle these bits to turn them into the right physical address. So that is something that's going on, and it's expensive and slow, and it's right now it's the cost we're paying. So yeah, there's a lot of work going on. As we'll see, it'll become more work soon, but then it'll become faster. Yeah.
Your example of physical parameters that you showed in the page table.
Oh yeah, they were arbitrary. I just what I did is I said, not completely arbitrarily. You're getting to this question of like, how do I choose things, which is a debate about free will and what inputs come into me, what inspires me to pick that virtual page 0 maps to 1 and 1 to 5 and 3 to 4. There's actually some logic to that. Like I often will put the heap and the stack, I'll switch their order in physical memory so you don't feel like somehow the heap and the stack have to be placed in some similar way in physical memory as they do in our virtual address space. But yeah, it's arbitrary. You'd think I would just give a simple answer once in a while. Why answer in yes when you can say much more and make people wonder why you're talking? So good. Other questions? All great questions. Thank you. Okay, so we're seeing how much we're suffering here, right? We're suffering. We're suffering because this is really, really slow. It's very slow. We've added hardware. The hardware is aware of the page table. It's really slow because it's turned our process of we were willing to pay the cost of a single memory reference, but now we're paying an extra reference every time. So it's slow. And then the other problem that we already hinted at is, so here are the kind of big problems that we have to deal with today is, yeah, it's too slow, extra memory references. And by the way, maybe this kind of gets at your question that you asked, one of your 16 questions. what what we uh, what we what we noticed here is there was a bunch of work. It was calculating an address, then doing a load, then doing the actual translation, which is switching the VPM bits to the PFM bits, and then doing the actual load of the data. And I tend to focus on just the loads and not the bit twiddling parts. Why am I focusing on loads so much? Why the other things seem like kind of like you said instructions. I mean, they seem like work. Why do I focus on the memory accesses so much? Because it takes the most time, exactly. Memory is far away and slow. Doing things like changing bits, processors do that really, really well, right? Processors are great. People who built hardware from transistors up have figured out how to flip bits really quickly inside the processor, so quickly that we can't imagine it. But going to memory takes a long time, hundreds of times longer perhaps than that. So that's why we focus on these two pieces, because this one extra load is like essentially saying you've made all memory references twice as slow in order to have this abstraction of a paged virtual memory. That sounds like a big cost. And as an engineer type, you should say maybe we should do something about that. So that's our first thing. It's too slow with this extra memory reference. And another problem with these simple page tables is that they're too big. And we already talked about this. Like I said, if you have a big virtual address space, like a 32-bit one, like we said, pretty quickly with a 4K page that we already did this calculation, that's roughly 1 million entries. If each entry is 4 bytes, just the typical size that you might actually see, that's a 4 megabyte page table. And if you're running 1,000 processes on the system, not crazy for a server class machine, 1,000 processes, then suddenly you have 4 gigabytes of memory being used for page tables. I mean, what a boring use of memory. Now, it's amazing today that 4 gigabytes, you still might say, oh, well, what's 4 gigabytes? Because machines are pretty big, but hopefully that sounds to you like a huge amount of space. Of course, we've been supporting 32-bit address spaces much longer than before we had 4 gigabytes of memory. So we were figuring out how to deal with them even before we had this much physical memory. But this is a huge waste, and we're going to figure out how to make those go away too. So why don't we do an early break? Over break, we will think about a technical question instead of something fun. We'll do something fun next time. Here's a technical question. What we're always trying to do in this class is we have in our minds the stuff that we type, and we eventually type C code. We don't operate at the level of the machine. Everything we're talking about here is abstraction. So what you're trying to do in your mind is map C code to how the machine is actually working. That's what you're trying to do to be a good understander, a good person who understands how systems work, is you can look at C code and see something about what's going on underneath the hood. And that starts in 354 and continues in here. So let's say we have a piece of code like this. We have a loop variable I, and let's say we go through, use that to some sort of, well, let's pick a size. I'll pick that in a second. Something like this. And let's say we're doing some sort of summation. So we have a sum. And we say sum plus equals, and we're accessing some kind of array of integers based on I. So A is an array that's declared somewhere of some size, and let's say we're going to access, I don't know, 2,048 entries. And then the question is, for you, is when we're running code like this on a machine with 4 kilobyte pages, is how many pages are referenced during this time while we run this piece of code. So that's our question. We'll make it a technical thing to think about during break, which kind of makes it feel like not a break, but as we've said in this class, things get worse. So let's take a break and think about that.